The domain of a relation is the set of values which the variable x can take on the horizontal axis. In this video, I want to show you how to state the domain of a function in a set notation. Let's look first of all at a number line here, which is the x-axis. The function begins with this point over here and it goes towards the right into infinity. It is represented by a dot, and this will start at a value which we'll call 3. So what's the meaning of this? This means that the set of all x such that x is greater than or equal to 3. That dot represents the fact that it is also equal to 3. So how would we write this in a set notation? We'll need to put a brace first of all, and then show that x is such that x is greater or equal to 3. And then we'll finish off with a brace to close it off. And here is an example of that type of set. You can see that from the coordinates over here that we are interested only in the -1, the x value, which will be on the x-axis. And our set of all x's here are such that x is greater or equal to -1. So how would we write this as a set notation? We'll draw a brace and we'll say that x is such that x is, and this time we'll say greater and equal to -1, and then we'll finish off with another brace. Now let's look at a different example. This time I'm showing you a set of an x-axis with a set of values, and this particular graph here shows you an arrow going to the negative infinity, but this time it has an open dot. This excludes the number 2. So we say that this is a set of all x such that x is less than 2. And we would show it in a set notation as, again, brace, and we'll say x is such that x is less than 2, because in this instance 2 is not included. In this example, our open dot is here on 4, and our x values therefore are all less than 4, not including the 4. There is another dotted line over here which says y is equal to -2. That shows you the asymptote, and it has nothing to do with our set notation because it's in the on the y-axis, and we're only interested in the x-axis. So our notation therefore will look like brackets x is such that x is less than 4, and then we'll do an end of brackets. Now let's do an example where we incorporate both of those open dots and a closed dot. All we need to do is to look at the x coordinates. The x coordinates are -1 and 5. So our interest only lies in 5 and -1. So that means that our value of x, the set of all x values, will be now somewhere between -1 and 5. So we write the brackets and we'll say x is such that -1 comes first, 5 comes after, and x is in the middle. But -1 is less, it's a smaller one, so -1 is less than x, but not equal to -1. And x is less than, but it could be equal to 5. And we ended off with a brackets. Now before I get to some harder ones, I want to do some really easy ones. Let's see if you can recognize the fact that in this particular graph there is no dot here, open or closed. Yes, there is a dot over here, but it has nothing to do with my x values. And here we've got also an arrow which shows you that this goes also into positive infinity. So on the left hand side we're going to negative infinity, all the x values, and all the x values keep on going right into the positive infinity. In fact, there are no boundaries in here. We say that x is a member of the real values, or we might say that brackets x is such that x is, and then we write this sign over here, which is a member of the real values, and the real values are shown like this. And what it means is that x can be any real number. So I hope that you can see that in this particular graph we've got the same situation. All the x values go into the negative and they continue on and on into infinity, and on the right hand side all the x values also continue into the positive infinity. There's no boundaries. The bottom part over here, which just shows you a dot, has nothing to do with the x-axis. So once more we write exactly the same thing. X is such that x is a member, that's a sign for member, of the real values, and we'll close it up. So it's a real number. When you look at this graph, we get arrows at every point, arrow, arrow, and arrow, and arrow, and arrow, which means these lines continue more or less into infinity. But there's one problem in there, is that dotted line. This dotted line represents asymptote, which means that x can have actually any value it wants except the one on the green line here. And that green line is represented by here x is equal to 2, and this green line is x is equal to -2. Our values of x are such that x cannot be 2, or it cannot be -2. It can be anything but 2 and -2. On this graph, once again, our function has arrows and it continues in either direction. The same thing for the bottom arrow over here. And you probably notice, yes, it has asymptotes. But there are two types of asymptotes over here. We are only interested in one. We're only interested in the one that goes through the x-axis. Don't worry about the other one. The other one is meaningless. And this particular asymptote tells us that x cannot be 2. And our set notation therefore will be x is such that x cannot be equal to 2. And that's all there is required here. And one more, the last one, just for fun. We begin with a dot over here, and that dot is represented by not -3 but -4, because that's the x value. So we can put -4 in here. This is where we begin our function, and this function continues into infinity. The other numbers here, -2 and -2, are not necessary, nor is this coordinate over here, nothing to do with it. All we want is from -4 onwards. So do you remember how we did that? We used the brackets and we set that x is such that x is, now x has to be greater. Is it equal? Yes, it's equal to -4. Now you may want to think of this as x is such that we start with -4 is less than or equal to x. If you did that, you would be also correct. It doesn't really matter which way you do it, as long as that inequality is correct. Well, that finishes the domain, but we should do now the range. So the next video, I'll examine the range set notation, but please subscribe and like so that you can both get that new video, and it also distributes my work all over the world, and I'd really appreciate if you could help me out.